Alright, I would like to talk about state feedback and output feedback control design. Here is our system, x that equals to ax plus bu, linear, y equals to cx. X is the state, u is the control input, y is the output, a is n by n, b is n by m. You have m inputs, and output is p by n. Output has p outputs. Alright, I will directly start with state feedback. First of all, state feedback means x is measurable. And our aim is to make limit t goes to infinity output to track a command. And I am going to assume command is constant. To track different time varying commands, you can use output regulation theory, maybe a topic for a different video. I am going to assume command is 0 and x is measurable. There are two controller types for this, for state feedback. One of them is feedforward approach, where you design the control signal like k1x plus k2c. This is the feedback part. This is the feed forward part. Here k is m by n and k2 is m by p dimensions. And basically for this first controller type, if you plug it to your system, you are going to get your closed loop system, which will have x that equals to ax plus b minus k1x plus k2c, or you can write it like a minus b k1x plus b k2c. The first step is to make this matrix Hurwitz. For example, you can use the LQR command or pole placement. Again, these are the topics maybe I can cover later. If basically AB controllable, there always exists a gain k to make a minus b k1 Hurwitz. So you should first check whether AB controllable, and then again you can use pole placement approach, linear quadratic regulator LQR approach. In MATLAB, for example, you can simply go write LQR A, B, Q, and R. It will give you your K1 matrix. Alright, so with this, you are going to make this Hurwitz. Now, if it is Hurwitz, then, and since the command is constant, this system will converge somewhere, right? This is what we need to analyze. So basically, let's find the steady state value of the states. For this set x dot to 0, you have a minus b k1 x infinity plus b k2c. I am now going to talk about the selection of k2. Now you can rewrite the same thing as 0 equals to x infinity plus a minus b k1 inverse b k2c. This is invertible. It won't have a 0 eigenvalue because we just made it Hurwitz. We choose k. Now, but we don't care about x infinity, right? So we mainly want output to follow the command. So I am multiplying both sides by c. So we have c x infinity, which is y infinity, plus c a minus b k1 inverse b k2c. Arranging things, you are going to have y infinity equals to minus c a minus b k1 infinity b k2c. Now, if this is identity, then output will converge to the applied command. So for this purpose, you choose K2 to make it identity, this. All right, so basically, this is state feedback with this specific control structure, feed-forward feedback. And first choose K1 to make this Hurwitz. Since command is constant, system will X will converge to an equilibrium point. Then we are characterizing this equilibrium point. Then from here we are finding y infinity, and then we choose K2, just make this identity. This was the first controller type that I want to talk about. Now I will shift gears to other controller type. Let me erase here. All right, another popular approach is integral approach. Basically, in this case, your controller has this form. And you have the z dot equals to y minus c. You can think this as z equals the integral of y minus c, integrator. Now, first, let's close the loop. Then I will tell you how to choose K1 and K2. X dot in this case becomes a minus b K1, x minus b K2 z. And z dot, I am just going to replace y with cx equals to cx minus command. Little command is, little c is for the command. Now you can combine these equations into one. And if you do so, you are going to arrive a minus b K1 minus b K2 c 0 x z plus 0 minus identity multiplied by the command. Now, if you now make this matrix Hurwitz by choosing properly K1 and K2, which I am going to talk momentarily, then since C is constant, this X and Z will converge to their equilibrium point. So let's analyze this equilibrium point by setting this to 0. I am only going to look at the second line of the equation. This one, 0, C multiplied by X minus identity C. So we have 0 equals to C x infinity minus C. Now this is y infinity. So if you make this Hurwitz, y infinity will be command. In other words, we are satisfying this for the case when x is measurable. So all you need to make this this matrix Hurwitz. Now let's talk about how to make it Hurwitz. Now I am going to rewrite this matrix here in this form. The same matrix can be rewritten as A, C, 0, 0, minus B, 0, and K1, K2. Let's call this A bar. Let's call this B bar, and let's call this K. This is A minus BK structure. If A bar, B bar controllable, that always exists again K. You can find using again, for example, LQR or for placement. A bar, B bar, Q bar, R bar. This will give you K, and basically just use the first version for K1 and the second version for K2, or simply you can implement, instead of this, you can implement U equals to minus K X Z as your controller. Of course, don't forget the Y minus C. Now, if you ask how the controllability of this relates to the controllability of the original pair, I also have a little fact for you on this. If regular AB controllable, and rank of A, C, B, 0 is n plus m, then A bar, B bar controllable. Okay, so basically you can either check the controllability of A bar, B bar for these before applying LQR, or you can check regular AB's controllability with and this rank condition. If they are holding, they hold, this is controllable. To wrap up, basically this is how you choose K1 and K2 together like this. And once you make this matrix Hurwitz, system will automatically converge to its equilibrium point. And this integral controller has better robustness to disturbances as compared to the feed-forward approach. So in practice, this is more widely used as compared to the other one. If you like, I can do a proof or something later. I now shift the gear to state feedback, from state feedback to output feedback. All right. Output feedback, basically, X is not measurable. The aim is the same, limit t goes to infinity, y minus c, 0. So only output y is measurable, and we cannot use X in the control design. All right, I would like to start with the feed-forward feedback approach, the first one. So basically, first, before even doing that, we need to have an observer, Luenberger Observer, to estimate the state. X hat dot equals to A X hat BU. This is the copy of the system with X replaced with X hat because X is not available, plus Luenberger gain L, which is N by P matrix Y minus C X hat. Once you have that, so we are trying to estimate the state so that we can mimic state feedback type of approaches. To see if X hat converges to unknown X, I am defining an estimation error, X minus X hat, and I am taking its time derivative. Basically what we have is AX plus BU minus AX hat minus BU minus L. I am going to write Y as CX minus CX hat. They cancel out with each other. We have A X tilde from these two terms. Likewise, from here we have L C X tilde, and we have A minus L C X tilde. Now, you are going to choose L to make this Hurwitz. Why? If this is Hurwitz, then X tilde will go to 0. And to do so, we can write if AC observable, you are always going to find L to make this Hurwitz. For this, you can again use the LQR command. For example, first of all, spectrum eigenvalues of A minus LC equals to the spectrum of its transpose. And if you take its transpose, you have C transpose L transpose. This is kind of similar to A minus B K form. So if you would like to use LQR, L equals to LQR, you put A transpose, C transpose, some Q, some R, and because of this, you put a transpose here. You are going to find your Luenberger gain to make A minus LC stable. You can also use pole placement. Again, linear quadratic regulator and pole placement is a topic of a different video. And once you do that, x tilde, basically your x hat will converge to x, because x tilde will die out, vanish, and so that you are going to recover the state. Let's, for the output feedback, I am going to erase some stuff. Let's keep these equations here. You need to implement this. L y minus c x hat, and you need to choose L to make A minus LC Hurwitz, because in this case this dynamics will die out. I just would like to keep them on the board. All right, now let's talk about what will be the changes for the first controller. In this controller, for state feedback case, we were using this. Now all you need to do is to replace x with x hat. X is not available. We can get x hat from here, so we need to implement this controller. If you plug this to the original system, you are going to get x dot equals to A minus B K1 x plus B K2 C plus B K1 x tilde. Remember, x tilde is the x minus x hat. And now I am going to combine this with x tilde dot dynamics, which is A minus LC x tilde. Now we can write these two equations more compactly like this. X dot x tilde dot equals to A minus B K1 B K1 A minus LC 0 x tilde plus B K2 0 C. What you are seeing here is the separation principle, right? This is an upper triangular matrix, meaning that the eigenvalues of this matrix equals to the eigenvalues of this and this together. So this is, again, separation principle. Basically design K1 the way we designed for state feedback, as if state is available to you, and design the observer gain L like to make this Hurwitz. Once you put things together by using estimate, basically this system will converge to an equilibrium point. And basically, since this matrix is Hurwitz, because K1 and L making it Hurwitz, we can analyze its equilibrium point 0, 0. Now you are going to get the same thing, right? So from the first line, you are going to get 0 equals to A minus B K1 x infinity plus B K2 C plus B K1 x infinity. From the second line, you are going to get A minus LC x tilde infinity. This is invertible because we made it Hurwitz. So this equation implies x tilde infinity is 0, which makes this 0. So you recover the same equation, same equilibrium point analysis we did for state feedback. All you need to do is to satisfy then this equation, minus C A minus B K1 inverse B K2 C. Choose K2 to make this identity so that Y will follow the command. So it is the same design. So this difference between state feedback and output feedback, first choose K1 and K2 the way that I showed you for state feedback, and then simply replace X with X hat and estimate your state through this Luenberger Observer and choose your L to make A minus LC Hertz. Now we are going to look at the other one, integral approach. I think you got the story. We have the same story for that. So for state feedback case, we were using u equals to minus k x hat 1. This was for state feedback, and z dot was y minus c. We are already using y, you don't need to change anything. Just since x is not measurable, change it with x hat. Implement this observer. Make sure you choose k1 and k2 as if you are doing state feedback control, and implement the observer. This will work. Now we can show, in this case, basically the story is the same, so I'm just going to write the end result here. If you write x dot, z dot, and x tilde dot together, the closed loop system, you are going to have a plus bk1, bk2, bk1, c 0 0 0 0 a minus lc, x z x tilde plus 0 minus identity 0 c. Once again, we have an upper triangular structure. Because of this, we have kind of this structure, meaning that if this is Hurwitz, which is it is, right? So you made it Hurwitz by choosing K1 and K2, the way that I showed you for the state feedback case, and A minus LC is Hurwitz because of this, so that we can do a transient as a equilibrium point analysis by setting them to 0. This is Hurwitz, this is constant. Now I am going to look at the second line. Second line is C multiplied by X minus this. So basically C X infinity equals to C, or minus C equals to 0. From here we have Y infinity is C. Now I will recommend one thing though. So the eigenvalues of this should be faster than the more on the left hand side as compared to the eigenvalues of this matrix for this integral approach, so that estimation error dies out faster, so that your system more or less will behave like state feedback. It will give a state feedback performance even though you are using this. So this basically, if this vanishes fast, then you kind of recover state feedback performance. So choose the eigenvalues of this matrix by tweaking the Q and R matrices, or if you are using pole placement, directly place it further to the left for the integral approach. And for the, if you remember, for the feed-forward feedback approach, closed loop system was this, x tilde dot, a minus bk1, 0, bk1, a minus lc, x tilde plus bk2, 0, c. So let's say if eigenvalues of, let's say this is the imaginary axis, this is the real axis of the complex plane. If these eigenvalues live around here, choose these eigenvalues further to the left so that observation error, this x tilde dies out faster. All right, let me know if you have any comments. If you want me to explain any of these more in detail, then we can go from there.